Did you know that time moves faster for your face than your feet? It may sound like a riddle or a joke, but it's actually a concept that stems from Albert Einstein's theory of relativity. So buckle up, because we're about to delve into the fascinating world of space-time, gravity, and the mind-boggling reality of our universe. Let's start with the basics. Einstein's theory of relativity introduced a concept that was revolutionary for its time and remains profoundly significant today. It's the idea that time and space are not separate entities, but instead interwoven into a four-dimensional fabric known as space-time. Now imagine space-time as a trampoline. When you place a heavy object in the center, it creates a dip, a curvature. This is similar to what happens when a massive object, like Earth, distorts the space-time around it. But how does this relate to time? Well, according to Einstein, time isn't constant. It can be affected by speed and gravity. This is known as time dilation. The stronger the gravitational field, the slower time passes. That brings us back to the original question. Why does time move faster for your face than your feet? Well, it's because gravity is slightly stronger the closer you get to Earth's core. So when you're standing up, your feet are closer to the center of the Earth and are therefore in a slightly stronger gravitational field than your face. This means that, according to the theory of relativity, time is actually moving slightly slower at your feet than at your face. It's an almost imperceptible difference, but it's there, confirmed by precise atomic clock experiments. So next time you're feeling a bit old, just remember, in the grand scheme of the universe, your feet are a fraction of a second younger than your face. As strange as it may sound, it's just another example of how the universe is full of wonder and mystery, where even the simple act of standing can warp the fabric of space-time. So, technically, your feet are younger than your face. Speaking of gravity, did you know that it is the only force that can't be blocked or shielded? It's a fascinating fact, isn't it? But let's dive deeper. From the microcosm of atoms to the macrocosm of galaxies, four fundamental forces rule the universe: gravity, electromagnetic, strong nuclear, and weak nuclear forces. Picture a bustling city where gravity is like the subway system, always running beneath the surface, connecting everything. It's the force that holds our feet on the ground, anchoring the moon in its eternal dance around Earth and keeping the planets tethered to the sun. It's the cosmic glue holding galaxies together, yet it's the weakest of all the forces. Isn't that a paradox? Next, imagine the electromagnetic force as the city's power grid. It lights up our lives, literally. It's responsible for everything from the glow of a light bulb to the rainbow's spectrum, from the static electricity that makes your hair stand on end to the lightning that splits the sky. The strong nuclear force? Think of it as the city's construction crews, holding the very fabric of matter together. It's the force that binds protons and neutrons within an atom, preventing them from flying apart. Lastly, the weak nuclear force, the city's waste management system, if you will. It's responsible for radioactive decay and nuclear fission, cleaning up after the universe's atomic processes. Now, here's the kicker. You can block or shield against the electromagnetic, strong nuclear, and weak nuclear forces. But gravity? It's the unstoppable metro system running through everything, regardless of the barriers. It bends the fabric of space-time itself, pulling objects towards each other. You can't hide from it, and you can't shield against it. Whether you're a speck of dust or a massive star, gravity has you in its grasp. Gravity, the unstoppable force, permeates through everything in the universe. It's the silent puppet master manipulating the cosmic ballet, and it's the one force we can't escape or hide from. From gravity to speed, did you know that you're moving right now, faster than you think? Let's take a moment to delve into the concept of cosmic speed, a phenomenon that is as fascinating as it is mind-boggling. At this very moment, as you listen to my voice, you, me, everyone, and everything around us is hurtling through space at dizzying speeds. Let's start with our home planet, Earth. It rotates on its axis, completing a full turn every 24 hours. Although it doesn't feel like it, this means that at the equator, you're spinning around at a speed of over 1,000 miles per hour. That's faster than the top speed of a Bugatti Veyron, one of the fastest cars in the world. But that's just the beginning. Earth isn't just spinning. It's also orbiting the sun at an average speed of about 67,000 miles per hour. That's nearly 93 times the speed of sound. Imagine a journey from New York to London in less than 3 minutes. And there's another layer to this cosmic velocity. Our entire solar system is also on the move. It orbits around the center of our galaxy, the Milky Way, at an astonishing speed of approximately 543,000 miles per hour. To put this into perspective, if we could travel at this speed in a straight line, we could reach the moon in just under 30 minutes. But hold on to your hats, because we're not done yet. Our galaxy, the Milky Way, is also moving through the universe. It's hurtling towards the constellation Hydra at a speed of about 1.3 million miles per hour. So the next time you're sitting comfortably on your couch, remember this: you're not just sitting. You're spinning, orbiting, and racing through the cosmos on a planet that's part of a solar system in a galaxy that's moving through the universe. Even when you're sitting still, you're racing through space at incredible speeds. Moving on from speed to space, did you know that 99.999999% of an atom is empty space? That's right. Picture an atom as a miniature solar system with a tight nucleus playing the role of the sun and electrons flitting about like planets. But unlike a solar system, where most of the space is filled with stars, planets, asteroids, and other celestial bodies, an atom is almost entirely empty. Now let's delve a little deeper. The nucleus of an atom, home to protons and neutrons, is incredibly dense and compact. It's surrounded by a cloud of electrons, buzzing around at varying distances. Yet, the space between the nucleus and these electrons is vast, almost as vast as the distances between stars in the cosmos. Astonishing, isn't it? But here's the catch. If atoms are mostly empty space, why doesn't everything feel empty? Why can't we just pass through everything? Well, that's where the magic of quantum physics comes into play. Electrons in an atom whiz around the nucleus at such incredible speeds and in a cloud of such uncertainty that they create an electromagnetic field. This field, though generated by particles that occupy a tiny fraction of the atom's space, is powerful enough to prevent any two atoms from ever touching each other. Thus, to our senses, matter feels solid. It's like the blades of a fast-spinning fan. They're separate and distinct, but spin so fast that they appear to form a solid disk. It's the speed of the electrons and their associated electromagnetic fields that give substance to the world around us. Our understanding of the atom has evolved over the centuries, from Democritus's indivisible particles to Rutherford's nuclear model, and finally to the modern quantum mechanical model. And with each new understanding, we've unraveled another layer of the universe's complexity and beauty. So if you removed all the empty space from human bodies, the entire human race could fit into an apple. Imagine that. The unending void is not out there in the cosmos. It's right here within us and all around us. From space to water, did you know that hot water freezes faster than cold water? Sounds crazy, right? But it's a peculiar reality that's puzzled scientists for centuries. This enigmatic phenomenon is known as the Mpemba effect, named after Erasto Mpemba, a Tanzanian student who observed this in the mid-20th century, though it was known even in the times of Aristotle. The Mpemba effect is not a universal rule and doesn't always occur. It's a finicky phenomenon, appearing under certain conditions and vanishing under others. Imagine taking two identical containers, filling one with hot water and the other with cold water, and placing them in the same freezer simultaneously. In some cases, you'd find that the hot water freezes faster. But why? What could possibly cause this counterintuitive result? Well, there isn't a definitive answer yet, but several theories have been proposed. One of them is the evaporation hypothesis. Hot water can evaporate more quickly, reducing the amount of water left to freeze. Another theory suggests that dissolved gases in the water could play a role. Cold water can hold more dissolved gases than hot water, and these gases might somehow slow down the freezing process. Yet another theory involves supercooling, a state where a liquid remains liquid below its standard freezing point. It's possible that hot water might be less likely to supercool, and instead, freeze more rapidly. Remember, these are just theories. The Mpemba effect is one of those fantastic quirks of nature that keeps scientists scratching their heads. It's a reminder of how even the most common things around us, like water, can behave in ways that challenge our understanding. So, the next time you want to freeze water quickly, try using hot water. You might just be surprised by how quickly it turns to ice. It's a simple experiment that brings the mystery and wonder of science right into your kitchen. Isn't that something?